So a month ago I decided I want to build a CNC. What I did have on hand was a sheet of plywood, some more thick multiplex plywood that I found on the street, some steel bars that I found on the street as well, and of course I had my 3D printer. Initially I wanted to buy a CNC, but I don't really have anything I need to machine right now, so I'm not really in dire need of one. I also was not super excited about any of the models that are available on the market. There are a lot of CNCs available from AliExpress. The typical models are 3018, 3020, 6040, but the problem with them is that the quality is not great and the rigidity is missing, and the components are not great either. So for best stability I wanted linear rails, and nothing on linear rails is really available under 1000 euro, and it's also like a lot of waiting time and possibly customs, and I felt like the actual components to build such a CNC cost much less than 1000 euro, so it seemed like it's worth a try. Before going to linear rails, I decided to give a try to the components I had on hand, the steel tube and the 3D printer that can print the bushings. I have no experience with CNC whatsoever, so just building my first CNC is of course a crazy endeavor. But I like it. So here I assembled my first version of Y-axis, and it doesn't go smoothly. I also decided to use threaded rod for driving it. Of course, as everybody on the internet has warned me, the threaded rod is terrible for this purpose. It's meant for fastening things, not for making things move along it. Here is a comparison of just a 3D printed plastic bushing and a 3D printed plastic bushing with a special commercial bushing inside, made from steel and POM plastic. The problem is that it moves in steps, so the resistance of plastic sliding on steel, special gliding oil added everywhere, is still too big. The thrust bearings on both sides here, but it's still like I can hardly move this by hand. So even with a wrench, it's a considerable effort. I think if I put a NEMA 17 motor here, it would not even be strong enough one-to-one to drive this. NEMA 23 will probably drive this okay, but the problem is that it moves in steps because of the big resistance. If this doesn't work, then I do have linear rails, 2 levels above this kind of stuff. So we'll see. For now I'm just going to disassemble and try these bushings. And so of course the bushings never worked. I didn't want to wait a month for parts to come all the way from China, so AliExpress recently started selling out of Poland. And they come surprisingly fast. In 3 or 4 days I have the parts. The trade-off, of course, is that the quality is not great. I mean, the price is good, and I mean, I don't expect commercial quality precision parts for 40-50 euro. But still, if I paid the same price, I think, but waited for parts to come from China, I would get better parts. Here I'm machining a recess on one of the plywood parts so that the lead screw can actually fit. I had no experience with lead screws or linear rails before this, so I didn't know how much space should I actually leave for everything to fit, and of course it didn't fit. So for rails it's easy. If they say it's 400 millimeter, like what I have here, then the length of the rail is 400 millimeter. But for the ball bearing it's a little different. There the length of the entire assembly is 400. These are the results for today. It's not tidy at all, but I was just tired of sitting on a chair all day trying to design something in Fusion and wanted to get some work done. And plywood is really forgiving here. Like, you imagine if this would be aluminium, it would not really be possible. I think this machine, I hope this machine will actually be able to machine aluminum parts when fully assembled. I mean, who knows, but I do really hope that will happen. And so for comparison, with the ball screw I can easily turn this with my hand, even though this isn't like 8mm shank. It still moves. And these linear rails, you know, they're not top quality. They don't actually slide down under their own weight, even when oiled. But they were a good price and quick delivery. So I paid 90 euro for 2 rails, 4 carriages and 1 lead screw with bearing blocks. And there's even a coupler. Now I'll just close this up and no one will ever know what a shameful mess this is. I switched for thicker plywood. This is 30mm multiplex birch. And it's surprisingly not easy to drill all the holes in the right place. I have a little test rig here that I'm using to test different materials for bending. This is 10 cm by 1 cm aluminum. This weight is about 4 to 5 kilos. And as you can see, the deflection is about 0.1 mm. And it's pretty repeatable. So if I put more load on it, so just applying another 5-10 kilos on top of here, we get it to 0.5 mm deflection. Here I have 3 by 2 cm piece of aluminum. So I placed it a little bit off center, but you can see that deflection is much less. I mean, even if I apply like 20 kilograms, it only deflects 0.3 mm. Extra centimeter of thickness really did a lot, even though the cross section of this material is 6 square centimeters. Cross section of this stuff is 10. Now this is just a plain 20 by 20 mm construction steel. And you can see that it deflects even less than aluminum, even though the cross section of this steel beam is much smaller than aluminum, and it's also empty.
inside is just 2mm wall thickness. And so if I try to put more weight on it, it's kind of performing a little better than aluminum. And it's also much cheaper. So 1 meter of this stock is 15 euro, and 1 meter of this is 5. This is a 3 centimeter thick multiplex birch plywood. So it deflected a tenth. So here I'm putting almost all my weight, and it's only deflecting 0.5 millimeter.
I think I'm going to go with just thick plywood for now, so I can get a square meter of this plate for 260 euro and a square meter of plywood for 80 euro. A sketch for my Z-axis plate in Fusion, printed it 1:1, glued to a piece of plywood, and now I'm machining recesses for the Z-axis ball screw to sit. I 3D printed the mount for my router that I already have, just a standard Makita woodworking router. And 3D printing is really not quite precise here, because at the bottom the mount has way more plastic. It shrunk, and as a result the holes are no longer parallel. It's more like a cup. 0.5 millimeter difference between the bottom part and the top part of the plastic mount. So I ordered another set of linear rails from the same supplier in Poland, and there's like a stark difference between all 4 carriages. Most of them are very loose, but one of them is very tight, and it's not even sliding. It feels like some of the bolts aren't round inside, so it's moving in. It's very hard to get it moving. I also didn't do a stellar job designing the Z-axis plate, so as you can see some of the screws between the small linear rails on Z-axis and the big bolts that go into the carriages on the back, they actually collide, and I wasn't able to put in 2 screws for the small rails. Here is my first test cut. I was really unsure how it will work, so I chose the lightest workload possible, engraving wood. Here I am setting the Z-axis to 0. And here is my first reel cut with an 8mm carbide end mill that I normally use for steel. The cut went well. I didn't set the 0 properly on the Y-axis, so it kinda hit the limit a little bit. My circle is not really a circle, it has one flat side. The dimensions also were imperfect, so it was off by 0.5 millimeter. Only in one direction, not in the other. So these cuts are actually made using those tiny drivers that they use on 3D printers. So I'm driving my NEMA 23s, those little tiny drivers that only take like 1 amp or maybe 1.5 before burning out. Here's what's going on in terms of electronics. I have 3 NEMA 23 motors. They are rated up to 2.8 amps and 1.2 Nm torque. They are 54mm long. Initially they used to be plugged into this board. So this is Makerbase MKS DLS V2. It is basically an Arduino Uno board, but with more convenient connections. The stock version of this board comes with 3 drivers. They get really hot, only work at 12 volts, which I used to supply over here with this power supply. And I didn't have these drivers at all. So it was just this little board, 3 motors, and it worked for wood. Then I wanted to get more torque on these 2 axes, and I installed these 2 drivers. These are GM556 drivers from AliExpress, €10 each. And they work okay. They're rated up to 5 amps. I'm only driving them at around 2, but they're actually taking even less. So it's funny, there is a table over here saying how much peak amperage they would take. But since I'm powering this with my lab power supply, I see how much current they actually use, and it's always under 1 amp total. Even when I move both axes, it's still under 1 amp. So the peak current table that's on them, it's not continuous current. So I can probably bump up the current settings here even higher. So here is how it's currently set up. I have this board, it's connected to a computer via a USB cable, and on the computer I have Open Build Control, which is a free program to run G-code on the CNC. Here is the power cord for the router that I plug into the vacuum. I turn on and off the router manually. When I turn it on, the vacuum comes on automatically. Since I needed to upgrade up from 12 volts to 30 volts that I have on my lab power supply, I added this step down. Here I have the incoming voltage from the lab power supply. It goes to the drivers, then to the step down to the Arduino board. Then Arduino board is connected to Z-axis directly through this little driver, and to X and Y axes through the big drivers. Let me quickly show you my workflow in FreeCAD. First I create a document, then I create a sketch, much like in Fusion, and on the sketch I make a 2-dimensional drawing. In this example, just a rectangle, a square with 20mm length of each side. I will pad this sketch to the height of my material, 14.7mm, and then I will switch to the path workbench, which is what's used for CAM in FreeCAD. Create a new job in here for this body. I don't need any offset for extra stock, and then I will set the origin to this point so that my material is in the negative Z. Add the tool that I have, 8mm carbide, and set the tool speed. This is horizontal speed and this is vertical speed for drilling. Give the name to my output file and change the format to Gerbil, which is what my control board understands. Now I need to create the operation to actually remove the material. And so I pick the operation that can take faces as an input. So I select 4 sides and say that I want to cut them from the outside, add them to the base geometry, set the step down to 4mm so that it doesn't go too deep at once. And now I can preview my toolpath, which looks reasonable. I can also simulate it. And then export it as G-code. The G-code can then be directly imported into the Open Build control. There I set the machine to 0 and click the start. The entire operation took just over 1 minute, and the precision is okay, so it's 2/10 oversized on one side and 5/10 oversized on the other side. So I had more problems with precision initially because I used OpenBuild's calibration tool, and it set my steps per millimeter to something like 100.1, while it should have been just 100. Then I just later went into the settings and manually set it to exactly 100, and I got precision of 0.1 millimeter on both X and Y. So you saw me cut out the dust hood. Here I'm cutting with my first dust hood, the second dust hood, but actually the current version of the dust hood that's on the router right now is the best one that I have. The plastic is just sides of a 5-liter water bottle. As you see, I attach my material to the bed with double-sided sticky tape. I'm using good quality Tesa tape, which doesn't leave any residue. It's pretty strong. The only problem with it is if the end mill touches it, then it kind of meshes it up, and it's hard to remove from the surface afterwards. Sometimes I even have to use acetone. But I think other tapes would have the same problem. Here you can see another version of the dust hood. This one didn't do as well. You can see the chips flying left and right. Here is what I have here in terms of rigidity. If I pull with all my force towards me, then I get a deflection of 0.5 millimeter on y-axis. And if I push on it, I can get about 0.4. For x-axis, it's better. If I push on it, I can get about 0.4 to the left and 0.2 to the right. I wonder why it's different. Probably because of the carriages being so weird on the back of the z-axis. Well, I think the answer is that machine does have sufficient rigidity to cut aluminum, but I need to dial back my depth of cut, and I also need to figure out chip evacuation. Because what's currently happening is that aluminum just gets clogged up on my end mill and it starts melting aluminum instead of cutting it. And then at some point the router just cannot spin the non-cutting end mill anymore. This is really damaging the router. So I'm going to pause the aluminum experiments for now. But I really like how the 4mm depth of cut went over here. So in all of the preparation I forgot to change the G-code from a wooden G-code to aluminum G-code, and so here it ran 4mm depth of cut. And it actually did a good job on this path and this path. I know it's advisable to use single flute end mills for aluminum, but mine didn't arrive yet. It's also good to have coolant blown onto the end mill with compressed air, but wood and coolant wouldn't work well together. I also don't want to have aluminum chips blown all over the place, so I would need to figure out some kind of solution here. That's all for today. Thanks for watching, and see you next time.